For over 1,000 years, Greek astronomy dominated the ancient scientific landscape. The geocentric Ptolemaic system, built on Aristotelian physics, was accepted as absolute truth. Passed from the Greeks to the Christians to the Muslims, it stood unchallenged. This was until, in a modest home in Basra, a single man brought it all crashing down. Ibn al-Haytham took up his pen and set fire to certainty. In his doubts concerning Ptolemy, he exposed the contradictions of the ancient model and dared to question the greatest cosmological idol of his age. Before the rise of experimental science, the world was explained only through philosophy, and there was no bigger philosopher than Aristotle. His ideas on matter, motion, and the composition of the heavens formed the backbone of how scholars understood the universe. Contrary to modern assumptions, Aristotelian physics was not mere speculation, it was predictive. And when combined with Ptolemy's mathematical models, it could forecast the movement of the stars and the planets with impressive accuracy. Soon, it was more than just merely a theory, it had become dogma. Aristotle's reach had extended beyond the ages. Even his views on optics, which we would revisit later, were treated as unquestionable law. When the Muslim world inherited the scholarship of the Greeks and the Byzantines, they preserved it with great reverence. But reverence was not enough. New kind of thinkers emerged, those not content with merely preserving and accepting the thoughts of those who came before them, but those who actively wished to challenge them, modify them, and cast them aside if they were found to be inadequate. Names like Al-Jahiz, Al-Biruni, Al-Khwarizmi, and Ibn Sina began to question the old authorities, and among them stood perhaps the most daring of all, Ibn al-Haytham, known in Latin as al-Hazan, a man not content with accepting dogma, but determined to prove and test it. The time in which Ibn al-Haytham rose was one of brilliance and transformation. The ancient Greeks were long gone, the builders of the pyramid only a memory, and the brief light of the Carolingian Renaissance had faded, leaving much of Europe in intellectual darkness. But across the Islamic world, the flame of knowledge burned brightly. From philosophy to astronomy, medicine to theology, the Muslim world was alive with discovery. By the 10th and 11th centuries, scholars were no longer content to merely preserve Greek wisdom, they were questioning it. The ideas of Aristotle and Ptolemy, once considered sacred, were now being re-examined, refined, and sometimes overturned. It was in this world of restless curiosity that in 965 AD, in the city of Basra, a child named Abu Ali al-Hasan ibn al-Haytham was born. In Latin, he would later be known as al-Hasan, a rendering of al-Hasan, but in the East, he was simply known as Ibn al-Haytham. He received his early education in Basra and started his career in civil service, but soon the call of science overwhelmed the routines of administration. His keen intellect and relentless curiosity drew him closer to mathematics, astronomy, physics, and theology. Soon he left his career in civil service behind and pursued knowledge full-time, debating with scholars, traveling across the Muslim world to broaden his curiosity and seek any knowledge that he could find. His growing reputation reached Egypt, where the Fatimid ruler Abu Ali al-Mansur invited him to undertake an ambitious project to regulate the flow of the Nile by constructing a dam near Aswan. Ibn al-Haytham studied the problem carefully, drafting detailed plans and calculations that remarkably resemble the modern Aswan High Dam built 1,000 years later. But after rigorous analysis, he concluded that the project was too ambitious for the technology of his time, and when he refused, Abu Ali's officials grew hostile. To escape their wrath, Ibn al-Haytham feigned madness and was placed under house arrest. His books and instruments confiscated. He remained confined for years until Abu Ali's death in 1021 freed him from captivity. Now in his mid-50s, Ibn al-Haytham took refuge in Cairo within the precincts of Al-Azhar University. There, free at last from political constraint, he devoted the rest of his life to pure science. These final decades were his most fruitful. It was here that he composed his magnus opus, Kitāb al-Manāẓir, or the Book of Optics. the first systematic study of vision, light, and perception. Ibn al-Haytham died in Cairo in 1039 to 1040 AD, leaving a legacy of over 200 writings on virtually all non-scientific fields at the time, 50 of which survive today, but his biggest legacy was an idea, a method, one that would forever change humanity and their pursuit of truth. Ibn al-Haytham was more than a brilliant observer. His book of optics, Kitāb al-Manāẓir, reveals a mind profoundly aware of what we now call the scientific method. Centuries before Roger or Francis Bacon, he described a disciplined process of discovery, data collection, forming of hypotheses, and then verification through experiment. He insists in all of his works that all theories should be tested, even his own. He conducted himself and used induction, experimentation, and data gathering with extraordinary precision. To prove that light travels in straight lines, he constructed dark chambers and perforated screens, letting sunlight pass through tiny holes, an early version of the camera obscura. Through these controlled experiments, he demonstrated that light moves linearly, not diffusely, as Aristotle had claimed. Regarding refraction of light, he wrote, "Visual objects are seen by us through light refraction across thick material such as water and glass are bigger than their real size." This was 6 centuries before Isaac Newton came to similar conclusions. But Ibn al-Haytham's curiosity did not end with optics. In astronomy, he wrote, "We must distinguish between what is apparent to the senses and what reason tells us, and never accept the word of another unless it is confirmed by experiment." In one remarkable study, Ibn al-Haytham turned his gaze towards the Milky Way. It had divided the thinkers of the time. Some claimed that it was vapor in Earth's upper atmosphere, while others claimed that it laid amongst the stars. In order to see what was true, Ibn al-Haytham looked at the Milky Way from different places at the same time and from different times in the same place. When he saw no shift or change in pattern, he determined that it must be very distant from the Earth and it must lay among the stars. In this way, Ibn al-Haytham showed a method that was centuries beyond his time. Curiosity knew no bounds with Ibn al-Haytham. Though chiefly remembered for his book of optics, his curiosity extended far beyond vision and light. He explored the rise of sap in plants, what we now call capillary action, nearly 1,000 years before modern physics described it. Light, however, remained his main fascination. He did not only study sunlight, but he also studied the reflection of moonlight, the shimmer of stars, and even the flicker of fire, seeking to understand the nature of light itself. He was the first to propose what today would be known as Snell's law, that the eyes perceive light due to reflection from objects. More on this later, but whatever he put his mind to, his method was the same: experiment and observation in unison. To test whether light travels in straight lines, he built simple yet ingenious instruments, 2 aligned plates with a tiny opening through which moonlight could pass. When he observed the image that formed on the surface below, inverted and sharp, he realized that rays must move linearly. From these experiments came the principle of the camera obscura, the darkroom projection that centuries later would lead to the development of the modern camera. In his triangle properties from the side of the column, Ibn al-Haytham turned geometry into a tool for engineers, builders, and archetypes. In a time when geometry only existed in books, Ibn al-Haytham brought it into the field. When surveyors today measure the height of a hill, they use a theodolite, a precise instrument built on the principles of sine and cosine. But Ibn al-Haytham needed none of that. His tools were simple: 2 staffs, the human eye, and the logic of proportion. He would begin by driving one staff upright into the ground and noting its shadow under the sun. Then, at a set distance, he'd place a second staff and mark where its shadow fell. By comparing the lengths of the shadows and the distance between the stars, he could form a right triangle and from its geometry deduce the angle of elevation of the sun or of any distant point, such as a tower or hilltop. Once the angle was known, he could use simple proportion to find the height of the object. If the staff's height and shadow were known, and the larger shadow or distance measured from the hill, then the unseen height could be known via a single multiplication. To measure land area, he arrived at a similarly elegant solution. He argued that irregular terrain can be divided into a set of triangles, and each triangle's area can be found if its sides are known, a principle dating back to Haron of Alexandria, which Ibn al-Haytham refined and formalized. He described how to measure these sides across uneven ground, how to factor in slopes, and how to link the triangles in order to get an accurate map of the land. He wrote that geometry must serve application. Knowledge has no value unless it may be put to use. Therefore, we divide the land into shapes the mind can comprehend, and from these shapes we derive truth from measure. Through such reasoning, he anticipated the methods of triangulation surveying, optical leveling, and engineering geometry, all with the simplest of tools and the sharpest of minds. His interests went deep into engineering and architecture. In Aqwal al-Abniya, he detailed how to design durable structures, fortresses, and canals, even proposing methods to regulate the Nile's floods and harness water and wind power for machines. Beyond his book of optics, Ibn al-Haytham's curiosity extended to every single field of the natural world. He wrote on meteorology, he wrote on astronomy, physics, geometry, and all of the different sciences of the time, and he displayed the same precision and method in all of his pursuits. In one remarkable treatise on the twilight phenomena, he examined the fading light of dusk and dawn, and through rigorous calculation and observation, he determined that the height of the atmosphere extended to about 10 miles. By modern measurements, it is known that 80% of the atmosphere exists in the troposphere, and this is about 7 miles in height. Ibn al-Haytham essentially discovered the troposphere nearly 1,000 years ago. He also explored the mysteries of the halos, rainbows, reflection, and shadows in his book, Burning Spheres. He analyzed how curved glass could concentrate sunlight to a point, what we now call the focal point. In this work, Ibn al-Haytham went far beyond his famous Greek predecessors. He describes in detail how inversion, magnification, and color fringes arise through refraction, all varied by direct experimentation. He didn't simply repeat what Euclid and Ptolemy had written. He tested them. In his commentary on their works, he corrected, measured, and refined their assumptions, always basing theory on observation. Even in the realm of physics, his insights were extraordinary. He studied the relationship between the weight of air and its density, noting that an object weighed slightly less in denser air, a clear anticipation of the concept of atmospheric pressure. He also noted that the motion of a body depends on its speed, distance, and time. And he also began to sense that gravity is a force that acts upon all matter, ideas that would not be formalized until centuries later with Sir Isaac Newton. In all of these keen insights, there is one thing that is always present: a man unwilling to bend to authority and wishing to test everything against the world itself. You may be starting to wonder that how can a mind so extraordinary, so ahead of its time, not be mentioned in the same breath as Einstein, Newton, Heisenberg, or Bacon? And you would be right to ask. Modern education usually tells the story from a single lens, that of the Western world, wherein knowledge arises in the West and only then does it radiate. But the truth is richer, older, and far more connected. Long before the scientific revolution, scientists like Ibn al-Haytham were experimenting, observing, reasoning with rigor that would define modern science itself. I have not even begun to reveal all that he achieved. His insights into optics, mechanics, and even the early principles that would later lay the foundation of thermodynamics. However, this documentary is not about the politics of forgotten history. It is about the mind that made such history even possible. So let us turn to Ibn al-Haytham's biggest intellectual triumphs, his refutation of the ancient belief that Aristotle held, which is that vision is produced by rays that are sent from the eye, and his bold challenge to Ptolemy's model of the cosmos. Long before the camera, before lenses, and before telescopes, thinkers believed that the eye sent out rays towards the world to see it. This was the theory of Aristotle, Euclid, and Ptolemy, a view held for centuries. Ibn al-Haytham dared to question it. In his monumental work, the Book of Optics, he argued that light does not come out of the eye. Instead, an image of an object goes through the lenses of the eye, forming a perception within, an idea that was radical, and many contemporaries rejected it. However, al-Biruni and Ibn Sina accepted and saw its brilliance. He also overturned the long-held belief that the mirrors made images by reflecting rays that come from the eye. He argued that instead, the rays rays stem from the object itself, and then from reflective surfaces they go inside the eye, thereby forming the image, a principle that we take granted in modern optics. His work extended to the problem of Ibn al-Haytham. Given a cylindrical or convex mirror, find the exact spot where an object will reflect into the eye. To solve it, he formulated a fourth-degree polynomial equation and used hyperbolic geometry, a solution so advanced it astonished the scientific community. In true Ibn al-Haytham fashion, as part of his work, he discovered techniques that he used to find the volume of a paraboloid that would later be called calculus. Ibn al-Haytham didn't stop there. He explored diffraction of light through air and water, experimenting with spherical glass vessels, a precursor to magnifying lenses. The straight line path of light, asking whether rays from each point of an object could reach the eye without overlapping, and how the brain perceives distant, detailed images. Why the distance, mass, and volume of objects can be perceived visually. The causes of eye diseases, including myopia, presbyopia, and astigmatism. General laws of reflection and refraction, establishing principles centuries ahead of Newton and Kepler. Through this rigorous method, Ibn al-Haytham laid the foundation of modern optics. His work influenced Roger Bacon, Leonardo da Vinci, Newton, and Kepler, a legacy that we can feel in every single lens, camera, and telescope that we use today. For over 1,000 years, Ptolemy's geocentric system, a model in which the Earth stood immobile at the center of the universe, had guided astronomers. Combined with Aristotelian physics, it seemed almost unassailable. The planets, the star, and the sun all followed predictable circular paths, and questioning the cosmic order was almost unthinkable. Yet Ibn al-Haytham was not content in following authority. He meticulously examined Ptolemy's calculations, finding in them inconsistencies and contradictions, and he compared his observations of the planetary movement with the predictions made by the Ptolemaic model and found inconsistencies too significant to ignore. He asked the same type of questions that guided his study of light. Do the planets truly follow the circular paths described by Ptolemy? Are the epicycles and difference a true reflection of celestial motion or merely a mathematical convenience? What is the role of observation versus inherited theory in the understanding of the heavens? Through this careful reasoning, Ibn al-Haytham displayed that Ptolemy's model could not explain the observed movements of the planets. Though he did not have the tools to overthrow it completely, nonetheless it was enough to make the famous physicist, astronomer, and philosopher Fakhruddin al-Razi just a century later think that geocentrism and heliocentrism are equally possible and supported by the data, leading to the first rudimentary heliocentric models by Muslims of the Samarkand Observatory and thinkers who thoroughly criticized Ptolemy, such as Shams al-Din al-Khafiri. By insisting on observation over tradition, Ibn al-Haytham challenged the cosmological idol that stood for 1,000 years. His critiques later inspired many Muslim astronomers and led to the eventual overthrow of Ptolemy in Europe. And with that, we come to an end on our journey on the great Ibn al-Haytham, his life and his works. He was a marvel of his time in every sense of the word. He was a skeptic, a scholar, and a true scientist whose influence we are only beginning to appreciate now. With that said, I will be covering many more of the great Islamic scholars of the 11th century who shaped our modern thought. So do subscribe, like, and share my content. Until then, you can watch my documentary on Abu Hassan al-Ash'ari and the formation of early Islamic rational theology over here, or you can see my dive into early Sufi literature and beliefs in my documentary on Abu Qasim al-Junayd and the early Islamic mysticism over here. But until then, this is all that I have for you. Stay faithful and Assalamu alaikum wa rahmatullahi wa barakatuh.